Welcome to lecture number 13 of irrigation and drainage lecture series. So, in this lecture we are going to talk about the measurement devices. Okay. So, how do we measure flow in streams and the pipes. So, which are concentrating on this water delivery system from canal to field channels. So, in this, so the first thing is, so before going into the details, let us know some basic terminologies of and also the hydraulic principles of flow. And then the first thing is the flow rate or discharge. So, this is a familiar term, it is the flow rate. So, which is the fluid flowing per second through a channel or a pipe. Okay. So, if suppose the amount of volume of water which is flowing through a channel or pipe per second or per unit time is called the discharge. So, it is also known as flow rate. Okay. So, generally the units are meter cube per second or liter per second, and then the velocity approach. So, it is the velocity with which the fluid is approaching the measurement device is called the velocity approach. Generally, velocity is mentioned or denoted with q divided by area of flow. So, suppose you have, so this is the channel, right. So, the fluid is flowing this channel. Okay. So, this is the area of cross section. Okay. So, this suppose you have measurement device here. Okay. So, it is flowing with q and towards the measurement device, and which has the channel has a cross sectional area of A. So, then q by A, which is equal to the velocity. Okay. So, then so, the next is a continuity equation, so which is very important when you are talking about measuring fluid at 2 points. Okay. So, 2 or several points, not only 2 points, but more than 1 point. So, you can use the continuity equations. What exactly the continuity equation is? So, this is the quantity of fluid flowing per second through a conduit. Okay, at all sections is constant. So, considering no loss from the system or gain outside the system. Suppose here you have a conduit, right. So, section A, so here section 1 and you get section 2, the 2 sections, and the fluid is flowing with velocity v 1 through the section 1 at A 1 cross section, and section 2 when you are leaving velocity v 2 at A 2 cross section. So, you have 2 sections, fluid is flowing through a conduit and there is no fluid which is adding across, right, or fluid leaving from the system, right, across. So, in this system, so we can use continuity equation, that is A 1 into v 1 at section A 1 will be equal to A 2 v 2 at section 2. So, the product of area and velocity at section 1 is equal to product of area and velocity at section 2. So, this is continuity equation. If you have more sections and then area into velocity at the third section is equal to q. So, whatever. So, the q that previously we have seen, q is equal to area into velocity. So, the fluid flow which is at section 1 is equal to fluid flow at section 2, because there is no addition of fluid or there is no loss of fluid from the conduit in that case. So, the next is fluid pressure. So, fluid pressure is very well known law called Pascal's law. So, this Pascal's law states that a fluid at rest or static or in motion, that means dynamic, exerts pressure on its surface, right. So, in a static fluid, the intensity of pressure at a point is equal in all directions. Suppose, so this is the fluid, right. So, let us assume that this is a part of the fluid, and when you exert force on top of the fluid, and when the fluid is in static position. So, the fluid pressure which is acting on the face of triangle AC is equal to the P, I mean the fluid which is acting on face AB and fluid which is acting on face BC. So, this in the static position, the pressure exerting within the system, right, is equally distributed or equal. So, suppose you have for example, a bottle, right, a bottle, and which has a fluid, and you have a piston, right, you have a piston here. So, this is all fluid, this is all fluid. So, the amount of pressure which is exerting on top, suppose if you take at any point here or any point, will be equally, right, will be equal. So, the pressure at this point is equal, pressure at this point equal, pressure at this point equal, and this is pressure at this point. So, the pressure P which is acting on top will be P, P, P. Okay. So, in static position, the pressure exerted in each and every part will be equal. So, this is the Pascal's law, and then let us go into the steady and unsteady flow. So, the steady flow here, if you see, so in an open channel flow, if the velocity, depth of flow and the fluid flow rate do not change with time. So, that is a steady, right. The flow is termed as steady, else it is unsteady. Suppose dV by dt, which is a change of velocity with respect to time, which is equal to 0, with change in depth with respect to time 0, change in flow rate, flow rate with respect to time equal to 0. So, whereas unsteady is all is not equal to 0. Okay. So, this is the steady and unsteady flows, whereas the uniform and non-uniform flows. So, uniform, when you are talking about uniform and non-uniform, which we are referring to the space, whereas steady and unsteady we are referring to the time. Okay. So, that is only the difference, and Bernoulli's equation. So, Bernoulli's equation states that a steady flow of an incompressible fluid, the total energy at any point of fluid is constant. Suppose you have the fluid which is flowing through a conduit, right, or any open channel. So, what happens that let us say this is section 1 and section 2. So, the total energy at section 1 is equal to total energy at section 2. So, that is, so this equation represents. So, generally the total energy contains the 3 components. So, the one is the pressure and velocity. So, this is the kinetic energy, and this is the potential energy, or the pressure energy, it is called kinetic energy, and this is the potential energy. Okay. So, at any point throughout this fluid flow, see the total energy is constant. Okay. So, that is the Bernoulli's principle states. Okay. So, then so the next is what is the specific energy. So, the specific energy is the defined as energy per unit weight of fluid, whatever the energy we have seen earlier in the previous slide. So, per unit weight is the specific energy. So, since we are targeting the fluid, right. So, there is the elevation, the energy due to elevation will not be come into the picture. So, the specific energy which is equal to h plus V 1 square by 2 g. Okay. So, then what is critical depth? So, it is the depth of flow when the specific energy is minimum, and the velocity of the flow is critical depth, is also known as critical velocity. So, the specific energy at critical depth is minimum. Okay. So, if you see here, suppose generally we use this terminology in hydraulic jump. So, let us say here it is a structure here. So, the fluid is flowing on top, and then which has y h w, right, headwater depth, and after that, so the fluid is falling. Okay, so it is falling, then after it is going to rise, right. So, here this phenomena, so this the energy is minimum at one point. So, the depth at which the total energy or the specific energy which is minimum is called the critical depth, or the critical depth. Then after that, the flow is experiencing this subcritical flow. So, then after that it is going to rise, and that is a that is a subcritical, and so here the depth still it is the minimum, but it is minimum. So, that is supercritical, and then after that subcritical. Okay. So, here if you clearly see in this case, so at H 2, that initial depth, head depth let us say. Okay. So, then H c is the minimum depth at the depth at which the specific energy is minimum. Okay. So, H 1 there is another depth. Okay. So, this is less than H c. So, here if you see the energy on x axis and height on y axis, right. So, then subcritical flow will be so this is the line where you get this is the line, the 45-degree line. You see it is a divide between subcritical and supercritical flow. Okay. So, here this is the which is the constant flow, right, and then this is called the E minimum, the energy, the specific energy minimum, and the depth, corresponding depth is H c, which is called critical depth, and then the region which is above the 45-degree angle, that is called subcritical, and the below it is called supercritical flow. Okay. And then so the next is the flow measuring devices. So, the flow measuring devices broadly classified into volumetric measurements, area velocity methods, or tracer methods. It is mostly we use this in measuring flow rate in streams. Okay. So, the volumetric measurements, so the tools or devices used to measure flow can be categorized into volumetric flow measuring devices, or those are notches, weirs, flumes, venturi meters, orifice meter, magnetic meter, or ultrasonic meter. So, these are volumetric flow. Directly you can measure the volumetric flow of stream, and the velocity measuring devices like current meter, pitot tube, and float, etc. Okay. So, and water level measuring devices like staff gauge, meter scale, water level sensors, ultrasonic water level sensor, etc. So, these things are very much required for measuring the discharge in the flowing streams. Okay. So, then the next thing is, let us see how to use these devices and what kind of principles they use, and we are going to see here in this slide onwards. Okay. So, here the volumetric measurement. So, in this simple we also call the bucket and stopwatch method. So, here the flow which is taking place is allowed through a pipe, right. So, there you can measure the volume of water which is collected in a bucket for a particular time interval. So, here the number of buckets divided by the total time will give the discharge. So, discharge is the volume of water collected in a bucket by time required. Okay. Suppose you targeted 10 minutes time. So, start the timer and wait for 10 minutes and get the volume of water which is been collected in a bucket during the 10 minutes time. So, that will give the discharge. So, this is not suitable for large discharge or open channel flow, because you have, for open channel flow you have to again concentrate the flow and allow through the pipe or something like that. So, here we mentioned. So, then you are abstracting, you have to abstract the flow in order to measure it. But this is very well accepted method for the pipes, small pipes. Okay. So, then the next is the area velocity method. So, in this the terminology indicates the area and velocity. So, we know the discharge which is equal to area into velocity. So, that is why this method is called area into velocity. It has two components, you have to measure area and you have to measure velocity, and then product will give the area will give the discharge. So, here, so this is the equation. So, for example, in open channels what happens? So, the channel cross section is, if it is regular cross section you can use this, but if it is irregular cross section, so you have to measure the velocity at different cross section, different points along the cross section, right. So, you need to trace the cross section, the first point you need to trace, because it is irregular, you need to measure the cross section, and the next is, so measure velocity at different cross sections, I mean different points along the cross section. So, here for example, so take a small section here, for example, here this is the section, right. So, width is W, right, and then let us say this is D1 and D2, there is two depths, okay, cross section, two depths. So, that average D1 by D2, that is average. So, that will give the depth, and so this will give the trapezoidal cross section, right, this is trapezoidal cross section, and then the velocity which is measured at 0.2 times d, and velocity which is measured at 0.8 times d, and average them, and then you get the delta q for, I mean the flow rate for this section. So, similarly flow rate for this section, flow rate for this section, flow rate for this section, and summation of all these small d q's will get the total discharge in the channel. And also if you have like the velocity 0.6 d, and you can directly use this instead of averaging 0.2 d and 0.8 d. So, we have another approach like velocity at 0.6 d and directly multiply it and get the dq value here. Okay. And then the next is the tracer method. So, in this method, so a particular tracer is being injected at the head end. Okay. So, then you are going to measure its concentration in the downstream. Okay. So, this is the simple principle, and based on the mass conservation principle you are going to estimate the flow rate. Okay. So, you are going to see how the flow rate is going to estimate it using the tracer method. For example, here, so in this tracer method, if you see the conservation of equation, right. So, the q naught, let us assume that this is the flow, right, stream flow. Okay. So, the stream is flowing with q naught, that is what we are interested in, we want to estimate q naught, and C b, which is the initial concentration of the initial concentration of the tracer in the flow, and q, small q is the rate of injection of tracer, right, this is the tracer, and C1 its concentration of the tracer concentration. And here at this point when you measure, this is, let us say this is a measuring point, and so this the total flow rate is q plus q, and the concentration is let us say C2. Okay. So, only we need these measurements, and now q naught is this is the conservation of equation. So, the initial concentration and the amount you are adding, so that will be equal to the total concentration, I mean the mix, this is the mixing formula. Okay. And q naught, which is equal to the if you can rearrange this. So, the finally you will achieve this equation q naught equal to small q into C1 minus C2 and C2 minus CB. Okay. So, this is the equation you are going to use in order to measure or estimate the discharge in a stream using tracer method. So, the next is float method, okay, surface float. So, this is I mean of course, is the rough estimation, but this is a very easy method. If you have float, for example, here the two operators, the one is the two persons are having an known distance, right. So, then the person in the upstream is going to leave a float, and he note the time, initial time, and he will find out how long it is going to take from this point to this point. So, it is simple, the distance velocity, you are going to measure the velocity, which is the distance by time. Okay. So, the mean flow rate, because if you see this open channels, so the velocity profile, if you observe, so the velocity at the top is highest, right, at the bottom. Okay. So, that is why, since the float is floating on the top surface, so it is going to experience the maximum velocity. So, then in order to estimate the mean velocity, there is a formula like 0.8 times the surface velocity or the float velocity. So, that you get the mean velocity. Once you get the mean velocity and knowing the cross section, so you can estimate the discharge. So, then the next is the current meter. So, this is also to measure the velocity of the flow. So, the current meter, so the current, the term indicates the current. So, that means the flow. So, flow also known as the current. So, that is why the flow meter or flow current meter it is called. So, in this, so these are called the cups. So, it has number of cups here mounting on the axis. So, this is the tail, right. So, you have to put this current meter into the stream, and so based on the flow, the cups are going to rotate. So, the number of rotations will give number of rotations will be calibrated against the flow rate, right. So, here if you see the person who is using current meter to measure the flow rate in the streams. Okay. So, the discharge, which is equal to the flow cross section multiplied by flow velocity. So, similar to the previous the method used. So, current method gives the velocity, and if you know the area cross section, it will give the q, which is equal to area into velocity. So, the next is the water measuring water depth measurement. So, water depth measurement here, if you see the staff gauge. So, if you go to the roadside or any streams, there is a staff which is installed in a gauging site. So, there you can clearly see the height of water in the height of water which is present in the stream. Okay. So, you can use the staff gauge and also the water level sensors. So, water level sensors it works on the resistance. So, so based on the resistance it knows the, and we can the signal can be converted into water level. This is also calibrated one, and here it is ultrasonic level sensors. So, if you see here emitter acoustic wave, it goes into this, and then a weak returning acoustic wave. So, suppose this is in a tank. So, so the difference will be converted into voltage, and voltage will give the water level, and this is also calibrated ones. Okay. So, then so next is the measuring structures. For example, here we are talking about notches and weirs. So, notches and weirs, here the rectangular notch, if you see. So, this is a rectangular piece of which is made up of metal, right. There is a gauge. So, with this gauge you will know the depth, okay. So, and the cross section. So, with this cross section, this is the rectangular. So, we have the equations. So, knowing the height h, right. So, you can estimate the discharge, which is a function of height, okay. And basically height, and there is a correction factor C D, okay, and also the length. So, the length of height and length of the wear crust. Okay. So, similarly, the if it is a triangular shape, this is called a triangular notch. Okay. And then so next we have trapezoidal notch. So, what happened in case of rectangular notch or right. So, the because here there is a contraction, end contraction. So, the velocity of flow, the discharge may be interrupted. So, if you have the triangular slots at the end and made it the trapezoidal one. So, then the discharge will be higher. Okay. Here the discharge will be higher, right. So, this is trapezoidal notch, and the step notch, if you have the flow rate which is varying too much, right, in the flow streams, and you can step notch can help even to measure the lower discharges and higher discharges in the same notch. So, the next is, the next are the wears, right. So, the wears. So, what is the difference between wear and a notch? So, notch are the devices are made up of mostly the metals, right, metal sheets or anything, and wears are made up of cement, concrete or something like that, because so wears hold the larger discharges, whereas notches holds to measure the smaller discharges. Okay. So, similar to the notches, we have the classification. So, mostly according to the shape of opening, here the rectangular opening, that is a rectangular wear, right, and if it is a trapezoidal opening and which has 4 vertical and 1 horizontal side slope. So, that is called superlative wear. Okay. So, and then the next is classification is according to the nature of discharge. Okay. So, the nature of discharge, here the regular wear, we have seen that the simple, there is a rectangular wear, and there is the submerged wear. So, nature of discharge here. So, H 1 on head end and H 2 on the tail end. So, in the both so here if you see, so both has the depth, right. So, both the head end of the wear and tail end of the wear, which both has the flow depths. Okay. So, this is a submerged wear, and the formula to calculate the discharge in both case almost same, but only thing in this case when you calculate, it should be like H 1 minus H 2, that is a height, the difference in height. Then also estimate Q here, and then combine the discharge will be used to estimate the discharge in a submerged wear. Okay, we are going to see that. And the next classification is according to the width of the wear, So, here if you see the narrow crusted wear and broad crusted wear. So, look at this is called a width, right. So, based on the width of the wear, they classified as narrow crusted. So, in this case narrow crusted wear. So, H 1, which is the depth above the crust, which is greater than 4 times the width of the wear. So, if B is the width, so H 1 is greater than 4 times width of the wear, right. So, here we do not follow that here, right. So, H 1 is less than 4 times the width of the wear here. And then next classification is according to the nature of crust. So, here the sharp crusted wear and ogee wear. Okay. The sharp crusted wear, the thickness, so the thickness like here. So, this one, so H 1 by 2, generally H 1 by 2. So, the sharp crusted wear. So, whereas in ogee wear, what happened? So, here the similar to the sharp crested wear, but at the tip. So, this is going to be maximum at one point. So, that is 0.115 h, So, up to that it goes maximum, then after that it follows a parabola. Okay. So, this is the whole thing, and generally this is used in spillways. Okay. So, this is one kind of wear, and then one kind of classification, then other classification. This is according to the effect of the sides, okay, emerging nappy. So, here if you see this suppressed rectangular wear, and whereas this contracted rectangular wear, contracted rectangular wear. So, here the ends are these are called end contractions. Okay. So, here the length of the wear will be equal to the length of the water which is staying on top of the wear, which is equal to the length of the wear. So, contracted rectangular wear. So, here the wear width the channel width which is less than the wear length. Okay. So, then the next is how to measure the discharge in the structures. So, that we mentioned, for example, you have a rectangular wear. So, how to measure the mathematically, how to estimate the discharge here. So, the very simple, if you see here, this is a rectangular wear. So, consider a small piece of the flow, that is let us say delta, so dH. So, that is a small. So, the area will be L into delta H, okay, and theoretical velocity will be equal to square root of 2 g H. Okay. And you use the there is a coefficient of discharge C d, this is the area and this is the velocity. So, that will give the discharge through the small element. So, in order to get the total discharge, then you have to integrate the whole equation, right. So, if you integrate it and finally, you end up with this equation q equal 2 by 3 C d L square root 2 h 2 g into h power 3 by 2. Okay. And if you are counting the rectangular the contracted end contractions. So, only thing the equation is same except because you have end contractions, right. So, on the both sides, which is 10% of this, but 10% of that. So, there is a 0.2 h. Okay. So, this way we can estimate the discharge through the wears, rectangular wear. Suppose you have a triangular wear. So, the triangular wear case, what happens? So, this is the triangular wear. The similarly, if we follow the same dH, right, this is the same dH. So, and dH into 2 AC. So, let us say, so you take this portion out. So, one portion A and C. So, this one is here, right. So, A and C. So, 2 AC. Okay. So, because 2 AC, so 1 and 2, the 2 AC, and so this is the length, total length you got, and dH. Okay. So, this is the area, and 2 into, so this AC, which is AC is equal to h minus h small h, okay, h minus small h into tan theta by 2, right. So, h minus, so the AC which is equal, this is a triangle the principle, right, the side principle you can use. So, 2 into h minus h and tan theta by 2 into dH. Okay. So, then velocity we use the same velocity equation. So, now combine the multiply the C d and put the same equation here, and then integrate between 0 and h equation, and finally, you will get the triangular wear equation for measuring the discharge here. Okay. And then, so the next is to measure the discharge through trapezoidal or superlative wear. So, here, so it has two components, one is rectangular wear, right, the other one is the triangular wear. Okay. So, both. So, that is why here we take this is discharge principle for rectangular and discharge principle triangular wear. So, this is total discharge. So, why this superlative wear is important, because in rectangular wear, so as I said, the main problem is the discharge because of these contractions, the discharge is going to be decreased. So, in order to avoid that, in order to increase the discharge, right, or without having any effect on these contractions. So, if you have the triangular openings, then the discharge will increase. So, that is the main thing. So, since it has both triangular and rectangular. So, that is why the discharge through rectangular opening and triangular opening, so will be the total discharge through the trapezoidal wear or suppletive wear. And then, so next let us see the problem here. So, suppose you have a rectangular wear, right, or rectangular notch which has a discharge of 0.24 meter cube per second. When head of water is 800 mm. So, find the length of notch, assume C D equal to 0.6. Okay. So, you have discharge is given, C D is given and head is given. Okay. So, then find out what is the length of the notch. Okay. So, Q is given, H just convert C D 0.6. So, you have this equation, rectangular wear equation, C D equal to 2 by 3 square root 2 G L H power 3 by 2. So, substitute these values here and you will get 0.189 meter. Okay. So, then we have another example here on finding the discharge over a triangular notch 60-degree angle when head over a triangular notch is 0.2 meter and C D is given 0.6. So, if you see the given values, theta is given, that is 60-degree and H head over the crust 0.2 meter and C D is 0.6. Okay. And substitute, this is the equation, if you remember this equation through triangular notch, right. So, C D is given. So, put the values, all the values and you will get the discharge as 0.146 meter cube per second. Okay. So, this is all about this lecture. So, mostly in this lecture we covered what are the main principles involved in flow measurement devices and what are the measurement methods. Okay. So, mostly the area velocity method, right, and discharge volume method and then tracer method, the float method. So, these are the methods commonly used in stream flow measurement, and in addition to that there are some structures like weirs, notches, okay, and then flumes. We are going to talk about the flumes in the next class, and then these are the open channels of course, but there are some measuring devices for the flow through pipes. We are going to see those things in the next class. Okay. Thank you.